We're continuing section 3.5, a factorial review. This is needed because we're going to go over an example of nth derivative, and in the solution to that, to see patterns, we're going to use factorials. What is factorial? N factorial, see n with the exclamation mark, is the number n times n minus 1 times n minus 2 times all the way 3, 2, 1. And this definition is for n bigger than equal to 1. And so this means that 1 factorial is 1, 2 factorial is 2 times 1 factorial, 2, 3 factorial is 3 times 2 factorial, 6, and 4 factorial 24, 5 factorial 120, n factorial, again, n times n minus 1 factorial, and it's just that long array of numbers multiplied together. By convention, we go 0 factorial equal to 1. And let's go do example 4. Calculate the first 4 derivatives of y equal to x to power negative 1. Then find the pattern and determine a general formula for nth derivative of y. So let's take the first derivative of y. By the way, if you have y to parentheses 0, that means a function itself. That's something that comes up in calculus 2 a lot. Y to power parentheses 0 is function itself, 0th derivative, that's the original. Then y to power 1, y to power parentheses 1 is the first derivative, and so that's negative 1 times x to power negative 2, that's negative x to power negative 2. What about y to power parentheses 2, that's the second derivative, that's negative 1 times negative 2 times x to power 1 less negative 3. That's 2x to power negative 3. And continue y to power 3. Again, another exponent comes down, and you end up with negative 6x to power negative 4 this time. You can see that the routine, you're just multiplying by these exponents. And you're starting from 1, and at every derivative, at every nth derivative, you go all the way to, so it's negative 1, negative 2, all the way to negative n. And so what happens is that I see these negative signs, and the number of negative signs matches the number of derivative, and I see a factorial that also matches the number of derivative, and I see an exponent that is 1 less than the number of it's negative n, the nth derivative minus 1, and so it becomes negative n to power n, for there are n many minuses multiplying together, and n factorial for all these numbers, the absolute value of these minus numbers, the negative numbers that are multiplying together, and x to power negative n plus 1 because of the exponent. Now, higher derivatives and implicit differentiation. We've seen implicit differentiation at this point. Now what we want to do to see if what do we need to do to find a second derivative using implicit differentiation. Find y double prime for the ellipse defined implicitly by 4x squared plus y squared equal to 9. So we know how to implicitly find y prime, right? So we take the derivative of both sides. The right side is going to be 0. The left side, we're taking the derivative of both sides with respect to x. And so the 4x squared is just 8x plus 2y squared is 2y times derivative of inside. What is inside? Y. Y is a function of x, so it becomes y prime. Now, two ways of going about doing the second part of this problem. part 1, you solve for y prime, and in here, and you get negative 4x over y. Then you take the second derivative, and it would be an implicit differentiation 2. Then from here, you take another derivative of both sides, and derivative of y prime becomes second derivative of y, which is y double prime, equal to, this is a quotient rule, and so it's a derivative of high minus 4 times y, then minus high, which is minus 4, times derivative of the low. And derivative of low in this case, is just y prime and over y to power 2. Now, what you need to do at this point is to replace y prime in here by the value from above. So minus 4y plus 4x times negative 4x over y divided by y squared. And a common denominator, and you get minus 4y squared minus 4x squared divided by y to the second. Now simplify this, and we end up with a negative 4y squared minus 4x squared divided by that y goes to the denominator, y to the third. Now this was the first method. What did we do with the first method? We solved for y prime and we took another derivative, but another derivative of y prime is y double prime, and then when I did that I had to replace, because it's an implicit differentiation again, I end up with y prime on the right side, and I have to replace that by over here. The other method is very similar to this. Basically it helps to avoid the quotient rule in there, and sometimes one is easier than the other, and your choice. So the other method, we're gonna not solve for 8x plus 2y prime equal to 0. I mean, we're not going to use the format that we solved, but we use the unsolved part to take another derivative. So take another derivative of this one, and in here you get derivative of 8x is going to be 8. Derivative of 2y prime is 2 times derivative of first one of these, which is y prime, times the second one, which is y prime, and then basically the first one times the derivative of the other one, which is y times y double prime, and then you set it equal to 0 because the other side is 0. Now two things to notice. First, y double prime appeared on the second time we took the derivative and we were expecting it. Other is that the y prime appeared twice, and you have to replace that value for y prime. So y double prime would be an implicit function of y and x, not basically no more of y prime. Y prime has to be solved in there. And so that's the next step. So we're replacing, we're solving for y double prime. Then we're replacing y prime for where we see y prime. And in here, we get the same answer as we did before. So solving y for y prime over here by subtracting 8 and dividing by 2, and then basically after that also subtracting y prime or y prime to power 2, and then dividing by y. And then over here we just replace y prime, and we got the same answer as we did before. Okay, so interesting part of this, if you look at the y prime and y double prime, and let's say if over here the concavity of the function only depends on the value of y. If over here, because the numerator is always negative, if the value of y is negative also, the concavity is up. If the value of y is positive, the concavity is down. So if y is negative, according to this, if y is negative, the concavity is up, which is, if the y is positive, the concavity is downward. Other things to notice, and it's interesting, if the y prime, if x and y are of the same sign, SIGN, then y prime is going to be negative, therefore function is decreasing. If they are not the same sign, the function is increasing. So here they are the same sign, and function is decreasing. And then here they are the same sign, function is decreasing. I'm sorry, the implicit function is decreasing. And that in over here, they are different sign, and implicit function is increasing, and over here they are the different sign, and the implicit function is increasing as well.